If the general functioning of radar satellites or the concept of spatial resolution is unfamiliar to you, then be sure to check out our introductory videos on these topics beforehand. Do you already have a basic understanding of radar satellites? Perfect. Then let's dive right into today's topic. The physics of electromagnetic waves not only opens up many possibilities for remote sensing, but also imposes certain limitations. These limitations suggest that radar satellites actually cannot function. Why? This can be derived mathematically and physically. If you want to record electromagnetic waves, you must direct them to a sensor. In our eyes, for example, light passes through the pupil before it hits our sensor, the retina. In a camera, it is directed through an aperture in the lens before the CCD sensor measures the incoming wavelengths of visible light and converts them into an image. This opening that the light must pass through is called the aperture in optics. How well an object in the distance can be imaged largely depends on the size of this aperture. Electromagnetic waves that pass through the aperture are deflected or diffracted. The physical principle behind this is known as Fraunhofer diffraction. This creates an angle that is crucial in determining how small an object can be for it to be imaged by a system. This angle depends on the size of the aperture and the wavelength used. The sign of this angle corresponds to the simple formula: wavelength divided by aperture. Radar satellites also operate with electromagnetic waves and have an aperture. However, since they have neither a diaphragm nor a pupil, the aperture corresponds to the entire length of the radar antenna. In the case of Sentinel-2, this length is 12.3 meters. The satellites are in an orbit about 700 kilometers above the Earth. To simplify our calculation a bit, let's assume the Earth is flat. But don't tell anyone. If you now assume an angle alpha, at which electromagnetic radiation reaches the sensor, depending on the aperture and the wavelength, a triangle is formed. We can divide this into two right-angled triangles, which allows us to treat them according to the laws of trigonometry. For this, we label the corners of the triangle counterclockwise with the capital letters A, B, and C. The sides opposite the vertices are given the same name, just in lowercase. Thus, angle alpha is at vertex capital A opposite side lowercase a. Now we can calculate the sine of alpha. Sentinel-2 uses a wavelength of 0.05 meters. Divided by an aperture of 12.3 m, this results in a sine of 0.04. In our triangle, we now have the sine of the angle and the adjacent side. So we are looking for the opposite side, lowercase a. A glance at our trigonometric formulas disappoints, because to find the opposite side of the sine of an angle, we need the hypotenuse c. Fortunately, for very small angles, the sine is equivalent to the tangent. So if we set the sine equal to the tangent of alpha, we can use the formula for calculating the tangent. A quick rearrangement of this equation. And we can already calculate the opposite side, lowercase a. 0.004 multiplied by the adjacent side of 700 kilometers results in 2.8 km. However, since this only gives us half of the total distance sought on the Earth's surface, we multiply the result by 2 again and get 5.6 km. This means that the Sentinel-2 should actually have a spatial resolution of only about 5.6 km. According to the technical specifications, however, they have a resolution of 5 meters. According to the laws of wave physics, this could only be achieved with an antenna length of about 5,000 meters. Such an antenna could not be sent into space by humans in the foreseeable future. So, have we just uncovered a massive conspiracy by space organizations? Are there neither radar satellites nor radar images with an alleged resolution of 5 meters? Yes, there are. Because fortunately, physics also helps to outsmart physics. The magic word is SA, which describes a sophisticated system of complex recording and processing methods. Like synthetic aperture radar systems, because they can bypass the problems of low spatial resolution and why they don't need kilometer-long antennas. For this, we will explain in the next video. But now you already know what an aperture is, why the aperture could theoretically be a problem for radar satellites, and how this problem can be demonstrated in a mathematical physical way. These principles naturally apply not only to radar satellites. As mentioned at the beginning, every other known optical system, from the smallest smartphone camera to the Hubble telescope, depends on them. However, visible light is in the shorter range of the electromagnetic spectrum. And with shorter wavelengths, higher resolutions can be achieved more easily than with the significantly longer radar waves.